You probably think your lure is bright pink, but to a rainbow trout swimming 15 feet deep, it looks completely black. What follows is the exact biology behind a trout's eye, and why UV reflection triggers violent strikes when nothing else works. Decades of research from visual neuroscientists like Dr. Craig Harishan have fundamentally changed how we understand what's happening beneath the surface. Here's something most anglers never stop to consider. You spend 20 minutes picking the perfect red crankbait off the shelf, you hold it under the shop lights, you admire how vivid it looks, and you tie it on with total confidence. But the moment that lure sinks past 15 feet, every trace of red vanishes. It doesn't fade, it doesn't dim, it's gone. To a rainbow trout holding at that depth, your carefully chosen lure is now a dull, featureless shadow. And that same trout can see an entire spectrum of light you didn't even know existed. To understand why, start with the eye itself. Humans have 3 types of cone cells in our retinas, detecting red, green, and blue light with peak sensitivities at roughly 565, 535, and 440 nanometers. That 3-cone system gives us trichromatic vision, and every color you've ever seen is your brain mixing signals from those 3 receptor types. Trout have 4. Their cone cells peak at 600, 535, 440, and 355 nanometers. The green and blue cones are virtually identical to ours, but that red cone peaks at 600 nanometers, compared to our 565, which means trout see deeper into the red end of the spectrum than we do. Colors that look like a dark fading maroon to you appear vivid and bright to a trout. In low light especially, a trout perceives red tones with far greater intensity than any human ever could. But the real revelation is that 4th cone, 355 nanometers deep into the ultraviolet range, specifically the UVA band between 315 and 400 nanometers, at a wavelength completely invisible to the human eye. Trout don't just see the rainbow we see, they see beyond it. Subscribe if you like fishing, like the video for a great catch. Now, why would a fish need ultraviolet vision? The answer comes down to food. During their first year of life, trout fry feed heavily on zooplankton, tiny organisms like Daphnia that drift through the water column. These creatures absorb ultraviolet light, creating a distinct UV silhouette against the ambient water. To a young trout with fully developed UV cones, zooplankton practically glow against their surroundings. UV vision isn't decorative, it's a survival tool. And it's how juvenile trout find food in clear water when there's nothing else to key on. And this is where the science gets genuinely fascinating, because trout don't keep the same eyes their entire lives. Research led by Professor Inigo Novales-Flamarique at Simon Fraser University revealed that as trout mature past roughly 2 to 3 years of age, their dedicated UV cone cells begin to disappear. The single cones in juvenile trout switch their opsin expression, shifting from UV-sensitive pigments to blue-sensitive ones. A 2007 study published in the Journal of Experimental Biology confirmed this switch, showing that it doesn't reverse in adulthood. So a 3-year-old trout measuring somewhere between 20 and 30 centimeters has functionally lost its primary UV receptors. It now operates on a 3-cone system, red, green, and blue, more similar to human vision, though still shifted toward the red end. Here's where it gets complicated, though. Some researchers found that UV-type cones still occupied 15 to 20% of the retinal surface area in sexually mature Pacific salmonids. The leading theory is that these dormant UV cones may reactivate during spawning season, when fish need every sensory advantage available to navigate, compete, and select mates. The late Dr. Craig Harishan at Queen's University in Kingston, Ontario, spent decades investigating exactly this phenomenon before his passing in August 2023. And his work established that UV photosensitivity in fish was far more complex and dynamic than anyone had previously imagined. Dr. Harishan's colleague, Dr. Shai Sabar, added another layer with research on polarized light vision in rainbow trout. Their 2013 study at Queen's University found something remarkable. Young trout detect polarized light using only the bottom half of their eyes, and as they mature, this ability migrates to the top half. The region of polarization sensitivity literally shifts during development. Trout aren't just reading color in UV, they're reading the polarization angle of light moving through the water. which helps them detect transparent prey, navigate using the sky's polarization pattern, and spot objects that would be completely invisible to an eye like ours. Research on similar fish found that polarization vision could double the distance at which prey was detected, compared to unpolarized conditions, double the sighting distance. That's an enormous competitive advantage, and it's built right into the anatomy. Now let's talk about what actually happens to color underwater, because this changes everything about how you should approach lure selection. Light doesn't penetrate water equally across the spectrum. Longer wavelengths get absorbed first. Red light with wavelengths above 600 nanometers disappears earliest. At just 5 feet deep, there's already a noticeable loss of red. By 10 feet, red is shifted to a muddy, rusty orange. At 20 feet, it looks dark brown. By 40 feet, red appears as a dark blue-green. And past 60 feet, it's black, just black. This upper band where sunlight still drives color, roughly down to 60 or 70 feet in clear water, is what limnologists call the euphotic zone. Below that, you're in the dysphotic zone where color is essentially gone and contrast becomes everything. Jacques Cousteau confirmed this dramatically during an underwater spearfishing expedition. This isn't theoretical. Divers have documented it directly. Blood from a wound deep underwater doesn't look red at all. It reads as green or dark brown, because the red wavelengths needed to produce red have already been filtered out by the water above. Only as a diver rises back toward the surface, passing through more and more of the spectrum, does that same blood gradually shift toward pink, then finally back to true red once they break through. Orange disappears next after red, then yellow, then green, then purple. Blue light penetrates deepest of all, and shorter than blue, ultraviolet penetrates even deeper. That's the critical insight. UV light reaches depths where visible colors have long since vanished. So a fluorescent lure that absorbs UV radiation and re-emits it as visible light is essentially creating its own color signal in a world that has gone monochrome. This is exactly why UV-enhanced lures trigger what anglers describe as violent strikes. It's not magic, it's biology. Many aquatic insects naturally reflect UV light, so a UV lure mimics something trout are already hardwired to attack. On top of that, UV creates stark contrast against the water, making the lure visible at distances and depths where a conventional finish would be completely invisible. The commercial fishing world figured this out before recreational anglers did. Pacific salmon trollers noticed decades ago that a near-transparent hoochie, specifically UV-enhanced hoochies with a ghostly purple tint, consistently outperformed brightly colored alternatives. That faint purple tint was UV fluorescence, producing results that nobody could explain at the time. Recreational anglers have since caught on. UV-treated spinners like the Mepsoglia with a UV-coated blade, or glow plastics designed to absorb and re-emit light, all operate on the same principle. So what does all of this mean practically? If you're fishing shallow water for younger, smaller trout, fish under about 10 inches, UV-reflective lures are hitting a visual system specifically tuned to detect them. These fish carry fully functional UV cones, and a UV bright lure mimics the zooplankton and insects they're already hunting. In this scenario, a small UV-treated spinner in gold or chartreuse, worked slowly through riffles, is an exceptionally well-matched choice. For larger, older trout, your brown trout and brook trout fall into this category as much as older rainbows do. The picture is more nuanced. Their dedicated UV cones have largely switched over, but residual UV sensitivity likely remains, especially during spawning periods. And regardless of UV, trout see red more intensely than you do. So in shallow water, red and orange patterns are stimulating a receptor far more sensitive than your own eyes would suggest. In murky water with reduced visibility, higher turbidity, go bigger and go redder. The contrast matters more than the subtlety. The time of day matters enormously as well. At sunrise and sunset, what anglers call the morning bite and the evening bite, the golden hours, the proportion of UV and blue light in the water increases relative to green and red. The angle of sunlight during those windows pushes more UV energy into the water column. And those are the moments when UV reflective lures gain their greatest advantage. If you're fishing UV gear, fish it hardest at first light and last light. The trout isn't seeing the same river you are. It never has been. It's operating in a visual world that extends beyond yours in both directions, deeper into red, and far past violet into ultraviolet. Every lure you tie on is a guess about what that alien visual system will respond to. The science just lets you make a much better guess.